And it's a very short introduction and very selective introduction as well. So, so that's all I can say. And many of these, it's the analysis was done with my let's say more programmer, data scientist colleagues. So very specific question, maybe I will not be able to answer all, but I'll try my best. So let's start. So let me start with some word cloud on machine learning. And this is one of the things I can get from Google. And it seems like they have so many different words or different buzzwords that come up. I try to look, but in this case, there's no words like health pop up, but like in a very clear way, maybe it's hidden somewhere. But let's say before we start, maybe if you like to talk or to chat, what are the words that you already heard about in this word crowd, or are there any words that you would like to learn more? Maybe you can type it in the chat. I can monitor it now on my smartphone, so I can have a look if you want. So maybe I'll give you 2-3 minutes to just type what you would like to learn more, or maybe what you already heard of and then still have no clue what it is. Deep learning, yes. Metadata. Oh, okay. That word, I'm not an expert in answering that, the terminology of it as well. Yes, artificial intelligence, external validation. Okay, we will talk about that today. AI, yes, of course. As data become big data. Okay, that is not in our talk today, but I probably will start with that. I think it's a good question. Predictive algorithm, yes, it's sort of there for sure. Not really exactly there, and I might talk about it in some way, but I don't say it out loud. But if we still have question about it later, then we can talk about it for sure. Random forest. Random forest walk. I don't know about it, but we will talk extensively about random forest. There exists the term random walk and random forest, but random forest walk, I will Google it after the session if there is there. Actually, we see the word healthcare here, so it's not very big, but it's on this left corner at the bottom corner. Okay, so let me continue. So I think probably maybe we should start with the word big data, because that's the one that I will not really cover in this talk, but it's one of the buzzwords for sure. So when the data is big, um, quite hard to say, I would say, depending, of course, on your computational power. If you think about the computer in the 60 or 70, the data that we all use today are all big for them, I would say. But the terminology, at least from the things that I learn or I know, we tend to think of it in terms of dimension. So big data can be the data that has a lot of data point. It can be like a very huge data with lots of people. So maybe it can be some kind of sensors or some other thing that contain a lot of information. Or maybe, how can I say that? Like, for example, for stock, then you have the stock price for every minute of that stock for the whole 20 years. So in that case, you have a lot of data. It can be in terms of time dimension or the number of people, the number of observation. But at the same time, another important aspect of big data is the variable that we observe. So for example, if we think about the genomic data, um, for one person, we already have a lot of variable in terms of the gene data. And then you compile that with 100,000 of people that attend UK Bio Data Bank. I think that's around 500,000 people. So all these 500,000 people with lots of variable of genetic data. So that's probably another example of big data. Right, but machine learning, you don't have to use it only for big data. like some, I think, sizable data that you feel like it has enough to do this kind of, let's say, training and testing of the model, that should be fine. But there might be some expert in here that can say to me like what might be the rule of thumb for the number of observation. Up to now, I haven't seen that. So like decent size of data, you normally can use it for sure. But the bigger, the better, because you need to train them, you need to do many, many things. And that's the things that I'm going to talk today. So 3 buzzwords: AI, machine learning, and deep learning. I will not touch very deeply into the definition of AI and deep learning. I will not pretend that I know best about that. But for average people or journalists, all of them are all the same. But to be precise, machine learning is just a subfield of AI, of artificial intelligence, because there are so many non-learning artificial intelligence out there. And at the same time, deep learning is just another subfield of machine learning, because there are so many things that we use. And probably I would say the things that I will present to you today, the method that I'm using, normally they are not really deep learning as such. So there are so many non-deep, non-neutral learning there that is classified as part of the ML. One of the nice definition for machine learning is this one by Tom Michel. And it said that machine learning is like a computer program that is said to learn from experience E with respect to some class terminology, right? Sorry, but let me just quote it. Some class of task T and performance measure P. If its performance at task in T as measured by P improve with experience E. Sounds really not really understanding, right? But let me just show you with some picture, and I will give you some example. The traditional programming is just the things that we have data and program predefined, and then we put it in computer and process it into some kind of output. But for machine learning, we have the data, and we say to the computer or to the learning process that this is the target, this is the output that we want, put it into some computer, then we got some kind of what we call program, or let's say selection of modeling or algorithm that we would use in the next step to get some best modeling, best output, or best representation of certain things. So as I quote here, machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. And what is it about this E, P, and T? Let me give you some example on that. So we said that improve on task T with respect to performance metrics P based on experience E. What is that? So let's think about the task of playing checkers. And the performance that we measure against is the percentage of games won against any opponent. So the experience is that playing practice game against the computer itself, or playing some kind of game to see what are the results of doing this and that move. Another example is like when we try to categorize email message as spam or legitimate. So the performance that we measure is like percentage of email message correctly classified. And then the experience is the database of email. And in this case, we can maybe have some human given the label that say like, this is the junk, this is not junk, something like that. And then it helped the program to improve. This could be like something like semi-supervised learning. We can talk about it later. Or something in healthcare that maybe you already heard about, like in breast cancer, you got the mammogram. Then the percentage of cancer patients correctly classified. This would be the performance or the things that we would like to maximize. Then the experience would be the database that the specialists already label images from all these database of mammogram. And then we let the machine learn and train on this. So just before getting started into the deeper part of this, let me just mention some difference between machine learning and statistics. So of course, machine learning based on many of statistic theory to process this, but there are some subtle difference, and then I just choose this from some, let's say, image Google on Google, and I think this one might be of our interest. So in terms of approach, statistic, think of it like there exists some kind of data generating process that underlie the relationship that we see in the world. For machine learning, it's just some kind of algorithmic model. For the driver of statistics, there are some theory, there are some math behind that. For machine learning, not all of them, but many of them, like, or most of them, is just about trying to best fit the data. The focus of statistics is about hypothesis testing and interpretability. So when you have some model, some regression model, let's say, then you check the hypothesis and you see and you try to interpret from that result. For machine learning, it's about predictive accuracy. So it has some kind of predictive algorithm that we use, and then we just try to maximize the ability to predict in that case. Data size, here they say like machine learning should be big data. I agree, it should be big enough, but maybe not like gigantically huge, something like that. And of course, machine learning is really helpful when it comes to high dimensional data. For example, if you think about trying to do a regression model, let's say, with 1,000 individuals, but then you already have information about them, for example, their genetic data, which contain millions, billions of information there. You can't just do regression and try to think about which variable are we going to use in this kind of thing. You need some technique that can deal with high dimensional data like that to select certain variable and use it in this 1,000 people or something like that. But in that particular bit, machine learning is quite helpful. Inference, in statistics, we talk a lot about the parameter estimation, the prediction, and also this kind of confident interval. You have this error bar or confident interval from the analysis. In machine learning, it's mainly about prediction. There are more about interpretable machine learning that I will show some example later. Model choice, yes, of course, we look at the choice in terms of in-sample goodness of fit and parameter significance for statistical model. For machine learning, of course, you might heard the term cross-validation of this predictive accuracy on partition of data. I will talk about that later. Popular tools are statistics. They claim that it should be R, this one, but you can think of it like SPSS data or even Excel for all other things. Machine learning also can do that, but many people like Python. The last one, I might not be completely agree. There are more improvement in the interpretability of machine learning later. It's more like a black box because you let the variable to be, how can I say, to be related, to be associated with the data in anyway. So it's not like this kind of simple functional form, linear form, like what we tend to do in statistics. Before I go further, let me touch a little bit. And I know that next year there will be a person who talk more about this. So I will just touch a little bit about data mining. So it depends on how you view this. But one ideas about it is like data mining is just to combine between machine learning and statistical analysis, and then get this to mine the data in order to get information, pattern, on the modeling that you want. And for that, to some extent, when you do this kind of analysis that we are doing in healthcare research or in social science that I'm more familiar to, then it's pretty much like we are data mining to some level. So the process of data mining and also to machine learning in general, the very long and lengthy process that we have to do is data pre-processing. When you have the data, you can't just throw anything to the machine and hope that it will learn and it will give you information. You have to cleanse it, integrate it, reduct it, and transform it in a way that it's suitable for your modeling that you are going to use or algorithm of machine learning that you are going to use. So when it comes to the analysis, of course, data mining, we can think about just machine learning is part of it, but also visualization or some data analytic. Or we have some kind of pattern evaluation to evaluate the patterns on certain things. And we summarize all this and try to represent it as a knowledge. And that's just about data mining that I want to touch. And I hope that next year we will have a presenter who will talk more about that, and I will gladly come to listen. So before I continue with some example of the research that I did in the past using some of these techniques, let me just quickly introduce the type of machine learning or type of learning that are out there that you might heard about. So the first one is supervised learning. So supervised learning, if I try to compare it to the things that maybe some of you might already know, regression analysis is one of the supervised learning in the sense that we tell the data that this is the set of independent variable that we are interested in. So we supervise and tell them to some level, label it to some level, and then we say that this is the outcome variable that we are looking at. Or something like classification, like in this picture, when we want to classify different types of picture for fruits, then we have some raw data, we have some training data set that we tell that this picture is pear, this picture is apple, this picture is mango, and then we train the model with these things. And then later on, we process them and evaluate them in another set of data in order to see if the model correctly specify this kind of output and classify things into apple, pear, and mango, how correct they are. And we measure the performance from that. I will give you more example on that. So in between supervised learning and unsupervised learning, sometimes people also talk about semi-supervised learning. So instead of label all everything by human, there might be part of the data that are labeled. So it's kind of like semi-supervised. So we give some instruction to some level. But when it comes to unsupervised, it's very data driven. So the things that we can think of is like to group something, grouping certain things, or cluster the data, or loads of data, like cluster some population into groups. The example that maybe you might be able to relate to is, for example, principal component analysis. This is to some extent an example of unsupervised learning. So we have some kind of raw data here, then the algorithm try to group them in this case, like group them into group, or we try to cluster them according to the look or different variable that we take. Another one that I wouldn't touch here because personally I haven't really have any research working on this is reinforced learning, which is about learning from mistake. So from this picture, you can see that agent kind of like act certain things towards the environment. And then the environment give back the rewards and kind of get the observation. And then for this thing, that agent be reinforced by reward or punishment and do certain action or adjust certain things and do new action and then get another type of reward or observation, and it's reinforced itself into that way. So that's probably all the type of machine learning or learning that I want to introduce you to that. I think that might be a good point to ask if there are any question or any things that might not be clear and you would like me to clarify more? Okay, so let me try to continue and see if there might be some more question or something later. So yes, when we try to design a learning system, what do we need to do? We have to choose some kind of training experience for them and then choose the target function. So for example, let's go back to this breast cancer mammogram thing. So the training experience that the machine would experience is to experience all this database of mammogram and the label by specialists. So then we have to choose the target function. The target function is to correctly identify which patient has cancer or not, right? So that's, in this case, we tend to identify it as 0 and 1. So 0, no cancer, 1 with cancer, something like that. And then we represent this target function, maybe by some kind of modeling or some kind of equation or certain things. And then we choose the algorithm or the technique to infer this target function from the experience or from the data. And to do that, we normally split the data into training set and test set. And the general assumption that we tend to have is that the, the training and test example are independently drawn from the same overall distribution of the data. So it's like identical, independent distribution. But there are some relaxation of this, of course, but this is just the standard way of doing this. So let me talk a little bit about this training set and test set in terms of the term cross-validation. So the idea behind cross-validation is that we try to measure the model performance. In this case is prediction accuracy of the model. Like let's say model M, measure with the out of sample prediction. So we split the sample into two random groups, like of a certain size, let's say N1 and N2. Sometimes people choose, let's say 70% of the data for their training set. So this is the in sample or training set. And the out of sample is the validation set, or all the things that we are going to check against. So maybe it might be like 70% or 80% of your data is for, or 90% of your data is for the training set, and 10% is the out of sample that you want to validate your model against. And maybe you can, like, there are so many ways to do this. There are one way that you do repeatedly do this k time in order to show to see the performance of the model. So what we are doing here, what we are doing here is just that we try to best guess the model from the in sample or the training set that we have. When we have that model, then we try to see how they perform against the validation set or out of the sample that we don't use to train the model. So let's say we have 10,000 observation of mammogram with the classification of having breast cancer or not. And then maybe we choose randomly 80% of them to be the training set. So the model would learn on this, like, this picture, this image that look like this is the one who has cancer. This image that look like this is the one who doesn't. So for that kind of learning, then the model creates certain things out of that, right? But then we try to validate this by checking with the data that 20% of the data that we don't use to train the model, and see how good it is in terms of the prediction. I can show you some numbers later. So let me come to the example that I did in certain research in the past, or yeah, try to do this thing with some other colleagues who use this type of machine learning analysis. So I will give two type of example for supervised learning, which is the one that I will focus on today, is about the things called random forest. Another one that I will talk about is unsupervised learning, which is about clustering. For supervised learning, there are two research topics. Two topics that I did for supervised learning is, the first one is about trying to find factors associating with workability index in OH population. So I use the word associating rather than affecting or impacting, because causality in machine learning is really tricky things and very debatable. So I would use more like association rather than causal for this type of research. But this is my strong opinion, that there are ways to imply causal from things, but you require a lot more assumption for that. Another one that I did or work on is about trying to find factors associating with probability of a person to gamble in the last 12 months. So that's the supervised learning. And I will come back to the unsupervised learning later. And it's like some kind of caution that I have. All graph and results here are preliminary and are intended for just like demonstration of the method only, so do not quote or use it anywhere. And some of them might even contain the language that you don't understand, because I just want to show you how the table look like, how the map look like, how the graph look like, rather than going into how to interpret things. And I will have some selling ideas about text analysis there at the end of this talk. Right, so let me touch into this workability index first. It's just the idea that we can measure let's say measure the ability of a person to work. And there are certain domain of question that you use to ask the person in a survey that they can answer, and then you would have some score for them, and then being able to classify them into groups. Like, for example, this one has, or this workability index that we used has 7 main domain. And each domain you just like ask the question like number of current disease diagnosed by physician, and then you have some score from it, or like number of sick leave in the past year, or some mental resource, or some work impairment due to disease, and so on. So this is some kind of questionnaire that you go out to ask, in this case, OH population, and then they answer you, and then you get this kind of score out of that. And in the literature, they classify this group into poor, moderate, good, and excellent. But then when you do this kind of machine learning training, sometimes it's quite tricky to get certain group distinguished from each other. So in that study, our team just decided to combine moderate and good together. So we end up to have only poor, middle, and excellent. So that's the way we did in that research. So before I go to the result and how to interpret, or what might be the nice graph that you guys might get from this machine learning research, or analysis, then let me just talk briefly about random forest. So random forest is one of the working horse of, let's say, many machine learning model, and then many research that you look at on PubMed or many other source, they would use random forest as the main model. So what is random forest? So let me start from a tree. So think about something called a decision tree. So if you want to answer uh, a question, or let's say to make some kind of decision about eating lunch, eating dinner, having some snack, or don't eat at all, what might be the rules that you have? So in this case, starting from hungry or not, if not hungry, then don't eat, obviously. And then if it's a midday, then midday, yes, then you eat lunch. Is it after 6 p.m.? Then if it's after 6 p.m., you eat dinner. If not, then you have some afternoon snacks. So this is just like a simple decision tree. But when we come to forest, the word forest means we have a lot of trees, right? So in that case, from a tree, we build, let's say from branch. So let's say there are some terminology there. So this circle here, the node here, they tend to call it leaves. And then all these arm, they tend to call it branch. And all this whole thing here, it's tree number 1. And then you have tree number 2, tree number 3. So instead of using just 1 tree, 2 tree, or whatever, you use a lot of tree. And then you use some kind of algorithm to make it do some kind of majority voting. So let's say you have the random forest model, and then you just have a person, one person there coming there with certain characteristic. And then the majority voting of those kind of characteristics say that, for this person, like going back to our question, so for this person, probably the best answer or the best thing for this person is to eat dinner, or that person is to eat lunch, and so on. Or maybe going back to the cancer question, the random forest, after majority voting, it can class people into having breast cancer or not having breast cancer. Another nice graph or the um, representation of random forest is probably this one. So you have so many trees, um, you use some kind of random subset of feature to try to choose what kind of tree it looks, because it depends really in this type of research. It depends on, if you look at, let's say, income first or age first or gender first, it could really affect the way the tree look like. So you random this kind of subset, and then, yeah, then the tree, each tree has some vote to predict the target class. And after voting this, then you reach some kind of final prediction. That's the rough idea of random forest. So in our research that we did in the past, we just want to classify people into 3 groups, like if they have poor workability index, middle workability index, and um, excellent workability index. And then our whole random forest that the data scientist gave to me looks very huge like this. Then if you look deeper into this, then there are certain characteristics, like there are summation of some health indicator. If it's less than 7.5, you go on the, for example, here that I expanded here, you go to the left arm. If it's not, then you go to the right arm. Then when you go to the left arm, again, the left arm asks you about health sum. Is it more or less than 2.5? Then you go on. But when you come to the right arm, now the question is about income. What are your income level? Is it more or less than 2,500 35 unit of currency or not? Those kind of things. So it has this type of decision rules that come into decision and make things and split the data until you get to the prediction that this number of people are in poor state of workability index. These are in excellent stage of workability index. So let me talk briefly about the precision or the performance that, like, there are many things that you can use to look at the performance of the model. But one of the things that people tend to use quite a lot is something called accuracy, or confusion metrics or whatever. So in this particular case, there are 3 different type of workability. So poor, middle, and excellent. So from here, the role is the number of people in each group as it is. So as you can see from the support here, there are 15 people from our data that are classified as poor in terms of workability index. 94 classified as middle, and 16 classified as excellent. This might not be the best way to classify it because you can see that the middle is really, really high, right? But this is just an example of the things that we did. So in this case, if you look at the matrix here, on top here, the diagonal thing is the one that the model correctly predict what really happened. So it said that out of these 15 samples that are in poor workability index, we got 6 of them right. Out of 94, we got something like 85 right. So this is quite high. That's why the precision and recall rate are quite high. Let me not touch into all these number, but it's just like a percentage of how good you predict it in terms of the number of prediction you make or the number of actual thing that happen. So in this case, we can see that the poor and the excellent workability index, the prediction that we get is not so great. We don't perform very well in predicting the number of people who are in poor or in excellent health workability condition. But for the middle one, we perform quite well. So it's 90% if you measure between the number 85 divided by 94. So it's roughly 90%. So that's pretty good. So in that sense, this is just the performance that we get from the model. So we know what we do well in terms of prediction or what we do not so good. And we have the overall prediction number or let's say score, which is 78 in this case. So out of the whole sample that we have, which is quite small, 125 people, we got 78% prediction right on average, let's say. Another thing that you can do after you get the model is to find the feature or the variable that are important in this model, has the highest weight or highest contribution to the score. In this case, this particular work has 2 different data sets that we are using. So the one we use both survey data and hospital record. That's on the left-hand side. The right-hand side one is just focused on hospital record only. Why did we do that? Because in general, you can conduct a survey to survey people and get that answer, right? And if you can do that, theoretically, you can even get the workability index directly from asking them and get the survey question answer. But if you can't do the survey, but you have the hospital record of that person, so this is administrative data. Can you use this data to predict workability index without all other things that you get from the survey? So in our case, the hospital record only model performed not so great compared to this all data use. So you can see that from this feature important that ranked by the importance of things, we always see this disease total. So it's like total number of disease that that person has that enter into the main feature important of the all model from this hospital record. So it's not really performed that great. But I just want to show that this is like what we did and probably can be done. So when you have this type of survey data, you just train and do the model with that and try to see if some of the data that you have, like administrative data, how well it can predict that, which in this case, we have to use the survey because the target variable come from the survey. The workability index is not the things that exist in hospital record. So that's why we need the survey. But for example, the breast cancer example, in that case, we already know the target or the outcome variable from the record. So probably in that case, maybe you might want to, let's say, classify people from mammogram, or you can even look at their hospital record on all the things that we have in their administrative data and try to predict if this person would have cancer or not. And then you come up with some predictive algorithm and try to evaluate it if it's good enough in terms of accuracy, what are the features that are important. And then these are the things that one thing that you can show in terms of feature important. Another one, and for this, another research that I choose is about this gambling in the last 12 months. So again, we have some kind of survey, and then people report about their behavior on gambling and so on. For this one, you can see that the model is slightly different. So we use between model called random forest and another one called XGBoost, which is this kind of gradient boost model. I will not touch about it, but just in this particular case, I want to show you this nice color that actually is just another representation of these metrics. So instead of represent it as number like that, you can let the program represent it as some kind of color. And this is the one that we call confusion matrix. And then here, a very, very small number here is like the percentage that you predict right. So in this case, the model predict quite well who would gamble. So it's like 93%, they got it right. But in terms of who wouldn't, they got it only 30%, so quite low. So in total, the classification accuracy or the precision of the model is just 64.8%. And in this particular case, we also want to show that this machine learning model, which has this kind of non-linear feature, might be better than the things that we would use. Like, let's say if you have this kind of yes, no question, some of you who might already did this kind of research before might think about logistic regression. Why don't we use logistic regression? In this particular case, we just compare. It's not always, but most of the time, because logistic regression is not as flexible. It's more linear and not as flexible and black box as machine learning. So in that case, the precision or accuracy of it is just around 63.8%. So 1% less compared to the model that we train and get it from the data. Maybe it doesn't work doing all this because it's just 1%, but in many cases, it can be more, much more in terms of the gain in prediction accuracy. And in this particular case, 56.8% of the sample that we have gamble in the last 12 months. So to be fair, our model performed better than the baseline. So if you guess that everyone gamble, then you would be able to achieve 56.8% accuracy. But our model achieved something like 64.8%. And we showed in this kind of confusion metrics. I show you the feature important in just the name and some kind of score. We can also have it nicely in the graph and compare it between different type of model. Like this one, we compare XGBoost, which is the machine learning one that we do, with logistic regression. And yes, as I excused myself before, this is the research that I did with other colleagues in outside of the UK, obviously. So the language is different. So, but I just want to show you that there are certain things that we can show with this technique. And sometimes, or I would say most of the time, or most always, there would be difference in this kind of feature important when it comes between random forest, XGBoost, or logistic regression. There might be difference in this, and then you have to make some kind of judgment. What would I tell the story of this? One of the problems that we tend to have in machine learning that people tend to complain is about interpretability. So it's quite difficult to other than say that this feature is important or whatever, but how can we show or interpret the model? Because machine learning is a little bit more like a black box. You don't see the equation on this is one of the independent variable with this kind of functional form and so on. So unlike logistic regression that you already set all that. So how can we make sense of this? So this is some technique called partial dependence plots that people start to use in order to make sense of the data. So in this particular case, for example, this is the relationship between age and playing or gambling or not. So in this particular case, the red line, which is the logistic regression, show downward trend. So the older you are, the less likely you would gamble. Of course, in this particular model, we add age as a linear model. Some people can add it as square term, cubic term, and so on. It would have some different look from here. But here we just want to show that this is the difference between linear relationship and the non-linear one that show that the peak, which is this dash line, which is around 56.8% that we, or 0.6% that we mentioned. Again, another one is about income per monthly income. And again, logistic regression by design, it's linear. So the more you earn, the more you play, the more likely you play, or the more likely you gamble. But for the model like XGBoost or random forest, which is not that much different from this graph, it shows this kind of step. So when you reach certain level of income, like in this case, around 29,000 baht, let's say, in this particular case, then the chance that you would play or gamble more is, or the chance that you would gamble in the last 12 months doesn't increase that much until it reaches this point where it has some strength jump. But you might have to be careful about this part, the very high income and the very low income, because it might be that our sample doesn't have that many people in that categories. And this could be the out of sample prediction that the model has. So we have to be careful when we interpret that. And then we combine these two impact together. Like what is the chance of playing gamble in the last 12 months when you combine the age and income together. So you have age here on the y-axis and income here on the x-axis, and then the lighter the graph is, the higher the chance. So you kind of see like it's the one who are in this age around 25 to 55 that has this light color, and at the same time it's the one who has a little bit more income who play more. But there are some difference in here. In this case, what we tend to call it interaction effects. In this case, it means like, seems like you combine these two graphs together. But in other case, you might discover something new. There might be certain group that are a little bit young, but very wealthy, and then they tend to gamble a lot or more likely to gamble. It might show something like that as well. But the bottom line is that I just want to show you different type of graph, different type of diagram that we can use to interpret or make sense of all these machine learning nonlinear. But let's think about it as some kind of group. So this is the classification that, or not classification, sorry, a clustering that we try to have the data, that we have a lot of data about how people gamble in different type of things like lotto, illegal lotto, casino, different type of sport betting, traditional betting, and also football betting, those kind of things. So there are different things that people can report. And then in this case, we use the money, the proportion of money that they use in this particular type of gambling. and then let the model design and cluster the people into different types. So for example, the first type are the one who play this type of gamble a lot, and it's the one that major play this one, and that's one type of people or behavior of gambling. The second one is the one who only pay lotto and illegal lotto. So half, let's say. The third one is the one who 100%, they don't pay anything illegal. They just play the legal lotto, and so on and so on. And that's the number of population that we get from weighted survey sample and so on. So my bottom line is that with all this behavior about gambling, you can classify people into the group of people who might be more into casino gambling, might be more into or all into illegal lotto or into legal lotto or into like football betting and so on and so on. So for all these things, we can have this group of people, classify them in this case based on the score that we use to cut off this kind of group. We end up with 8 groups. And what can we do with this? And again, this is Thai language all over, but then we can just look at each group. For example, this is group 4. That is probably the only thing that you can read here. Group 4. And we can look at how does the age distribution in this group look like for this group who are into doing this boxing, gambling, and also lotto and illegal lotto mainly. How does the age distribution look like? What are their occupation? How does they distribute across different province in the countries, and so on and so on. So there are quite a few things, or like income or other things that you can look at the characteristic or the average characteristic of this group. And then maybe you can say something like, so when we talk about this group of people who are interested in this setting or like gambling in these 3 things, boxing, legal lotto, illegal lotto, then these people look like this. They are more male, they are more a little bit older group, and so on and so on. So that's the things that probably we can say after we do all this clustering and can make sense with the data. The nice thing about clustering is that you don't need to tell the data how many, okay, maybe you need to tell like how many clusters you want, or maybe you have to come up with a way to combine with the number of clusters, let's say. But at the very end, the data decide itself, like according to the things that you give, like proportion of money that people gamble in different type of gambling, so and so on. So that kind of thing. Right. So that's all to research that I did using some of these machine learning techniques. And now it's more selling things, because when I prepare this presentation, I found this nice text analysis tools from other researchers. And I think it might be useful in health policy analysis. So what they did is like, for example, in this case, they analyzed the presidential inauguration speech of the US from George Washington to Donald Trump, and try to cluster them based on some score that make the text or the tone of the text similar. And then you can see that here things are more closer with this group that are cluster, or it's another type of cluster which is called hierarchical clustering. So it's like you just try to cluster things, and then you can see how each speech are clustered closer to which year, and so on. So I just think like maybe this kind of text analysis might be useful for some health policy when you think about Department of Health minister speech or whatever, or it might be useful. And other than doing this, there are some other nice things that people use in this kind of text analysis. Like, for example, you can evaluate if the tone of the speech is positive or negative. Like for this one is maybe about some kind of Twitter result, and then they try to see if this term is more, or this, for example, like central bank announcement or some Twitter thing, how much is the positive or negative terminology that are used in the data. Then you can also group them by topic. Like this one is just the one that come from newspaper website during 2016. So you can see the topic that are gathered together, like oil, Syria crisis, climate change, Clinton, doctor, and so on. And you still have some names of president candidate at that time, and all these topics that are grouped together in different groups. And then you can use this kind of like topic one, like oil group together with market sales price and so on. This is like the group of topic from these news reports, right? And then when it comes to climate, it's like water, energy, food, China, Chinese land, and so on. When it comes to refugee, you have the terms like Brussels, French migrant, Greece, negotiation, and so on. So those kind of things that we can also see from the data and group it from the data. So I think that's just a nice idea. And what I want to say here, because I still don't have any research like on this, but I think it might be interesting to throw to the group here, that if you can think of any important text or speech that come over time that might be interesting for health policy of your country and so on, yeah, you can discuss with me, and maybe we can think about how to use that in this text analysis and come up with something on how similar it is in terms of the way they say it when you cluster it, or how positive, negative it is, or what are the topics that we can gather. That's pretty much all. And then yes, you can also have some nice graph and then highlight only the negative term, or highlight only the positive term from the frequency and the popularity based on Twitter or whatever.